Welcome to Managing Data Leakage presentation, where we will be talking about mitigation and prevention techniques. My name is Arawa. I go by the pseudonym Arawa E. I am a graduate at the University of Maryland Global Campus, studying data analytics. As you may or may not be aware, data analytics is machine learning is a subcategory of data analytics. And that is my targeted concentration. I am the main event organizer for Miami Machine Learning, PyData Miami, and Scale Up and Network Orlando. Okay, so let's just get into the presentation. Okay, what is data leakage in machine learning? Data leakage in machine learning, according to IBM, is a type of error that causes a predictive model to look accurate until deployed in its use case. Then it will yield inaccurate results, leading to poor decision making and false insights. Okay? So there are two main types of data leakage in machine learning. There's target leakage and train test contamination. This presentation will mostly focus on target leakage. All right, so data leakage causes. There can be different causes for data leakage. Some include inclusion of future information, inappropriate feature selection, external data contamination, data processing errors, improper normalization, validation, and process changes leakage. So the type of cause determines if the model will underfit or overfit as a symptom. So data leakage is correlated to underfitting and overfitting depending on the symptoms, depending on the causes, So for example, inclusion of future information will have overfitting as a symptom, while inappropriate feature selection, like selection of features with little to no correlation to the target feature, will have underfitting as a symptom. So here lies the relationship between data leakage, underfitting, and overfitting. So let me briefly define underfitting and overfitting. According to IBM, underfitting is a scenario where in data science where a data model is unable to capture the relationship between the input and output variables accurately, generating a high error rate on both the training set and unseen data. And overfitting is the opposite, where the model has no correlation to the data and contains too much complexity, resulting in high accuracy of the data. I apologize. So overfitting is the opposite of underfitting, a scenario where a model has been overtrained and contains too much complexity, resulting in high accuracy of training data. So inclusion of future information and external data contamination, inappropriate feature selection are types of target leakage. And data processing errors, improper normalization and validation, and process changes leakage are types of train test split errors. So prevention techniques. So to prevent data leakage, organizations must engage in careful data handling and systemic evaluation. So some of these prevention techniques are appropriate data testing, proper feature engineering, and regular model evaluation. So appropriate data preprocessing means that we are cleaning our data properly, making sure our features are at least a little bit correlated to our data, and we are removing uncorrelated features out of our data. We don't want to over-complex or make our model too complex. And proper feature engineering means that we are ensuring that our features that we are creating do not contain future information. And we'll talk about that more later. And regular model evaluation means that every step we're taking, we are searching for symptoms of overfitting and underfitting. We're searching for symptoms where our features are including future information or target information. Okay. So, proper evaluation. Before model training is required to minimize the possibility of data leakage. So a few tools that we utilize to ensure proper evaluation is cross-validation, feature importance, and asking our experts. So for cross-validation, especially for time series data, where irregularity can obscure patterns, cross-validation can highlight potential leakage. So strict data handling and cross-validation play an essential role in LLMs, for example. So to avoid undermining a model's ability to respond to new input, we have to make sure that we are cross-validating our data sets before we test them. So, and then we move on to feature importance. So here we have a little snippet of feature importance of a data set. So creating a visualization such as this can highlight dependencies of a model on features that have unpredictable availability before the model is trained. Or it can help us determine that a feature is too unrelated to our target variable and should just be removed from our model altogether. So these visualizations can expose anomalies indicative of leakage. And also we can ask our experts. Machine learning experts or senior data scientists can scrutinize features and correlative visualizations before training and identify models that using unrealistic data that might not be predictably available after model deployment. So here we are talking about an example. We're going to focus mostly on target leakage today. So an example of a target leakage in a model is when we create a model to predict cancer, but it contains a field with levels of regression, which is usually assessed after cancer has been detected. So that field or that feature, cancer regression, introduces future information that would not have been available in a real-world case. Therefore, it would lead to overfitting, and in this case, the model is overfitting due to the regression giving away classification of malignancy. Okay, so, detection techniques. According to IBM, detecting data leakage requires organizations to be aware of how models are prepared and processed. It requires rigorous strategies for validating the integrity of machine learning models. So one of our detection techniques is the prepare, search, test. And this refers to the proper procedures to handle the machine learning pipeline. So for the prepare stage, this consists of properly splitting the data into training, cross-validation, and testing sets. If we do decide to use normalization on our dataset, it must be done separately. So for our training set, we would normalize on our training set separately from our cross-validation set and from our test set. Because if we were to normalize the whole dataset in one go, we would be introducing our test set to our training set, and it would cause data leakage. So unusually high performance during testing is also an indication that there's been data leakage. Before testing, we need to conduct a search and investigate suspicious patterns and reduce weights or drop features altogether of unrealistic or unavailable features. Another indication of data leakage is unexpected model behavior. And we'll talk more about that when we go through our code. So here we are. So mitigation techniques. Some mitigation techniques, if we were to create a model that already contains data leakage, we could monitor correlation of all engineered features. Well, this prior to testing or prior to training, that's just a prevention. Monitor correlation of features post data transformations, such as scaling normalization features, and we've talked about that. We would have to go back and drop features that introduce future data. So if we were to create a model that contains data leakage, we would use our visualizations, our feature importance, to figure out which features is introducing new future data or is the cause of the data leakage, and drop those features. So we might have to go back and through the revalidation process and start all over. So one way to ensure that that doesn't happen is to make sure we're not rerunning our partway running our validation, our cross-validation. So if during cross-validation we expose the model to our test set, then we have to start all over and retrain the model all over again. So if it is not possible, if we have a feature that introduces future information, but for some reason we need to keep it, one mitigation technique is to reduce the weights with regularization. Okay. So it is not always obvious that a certain feature will not always be available after a model is deployed, so it's always important to recheck and ask the experts to ensure that we don't fall into that trap. All right, so now we can go into our code. All right, so this notebook is to help us demonstrate how an engineered feature containing future information creates a target leakage pitfall for data leakage, so that it inflates performance metrics that poorly generalizes to new data. And for further background, you could always read What is Data Leakage in Machine Learning in IBM by Tim Mucci. Okay? So I'm just going to quickly go over how to connect to Kaggle, because we're using a Kaggle dataset from Google Colab. We're not going to actually connect, but I thought it would be a good exercise to kind of just quickly run through that. So here we are creating a connection to Google Drive from our Google Colab. We're installing Kaggle. We create a Kaggle directory, and we copy our, okay, so when we're doing this, we have to go to Kaggle, our kaggle.com, and go into our settings and create a token under API. So when you do that, a JSON file is downloaded and you save that to your Google Drive. You copy and paste the directory to your Google Drive here, and this is copying the JSON file to a local folder here on Google Colab. And now we're ensuring here that, oh my God, we're ensuring here that only the user, only the person who created the Google Colab has access to the kaggle.json file. Okay, and here we're extracting the dataset using the username from the kaggle.json file and our preferred dataset. Okay, so we are not doing that today, but I did want my members to have access to how easy it could be to connect to Kaggle. So I already have the employer's dataset, which is the dataset we're using for this demonstration here, and we're just going to import with pandas. So we have our dataset, we have our data frame.head, and it looks good. Okay, and so now we're going to engineer a feature that contains information from the target. Our target is salary. We're trying to predict what the salary is depending on the features given. So it is important to note that, oh, okay, let me explain this part here. So we're engineering a feature called end of year evals. And this feature will be containing information from our target, which is the salary. Okay, and it is important to note that end of year evals obviously will not always be available in deployment. So this is a feature that makes it a great. This is a feature that is a great example for data leakage. Okay, so the approach I took to create a feature that introduces future information, such as the salary column, is by taking the minimum and the maximum of salary, right, and dividing it by 10, because I want to simulate a correlation to salary with an eval structure that goes from 0 to 10. So here, just making sure I ran that. I'm going to run this again. So here we have the minimum, which is 25,000. We have the maximum, which is 215,000. And so our ideal correlation split is 19,000. Okay, I'm rounding up to an even 20,000 to simulate an eval structure, like I discussed earlier, from 0 to 10. So here we are, and here's our eval structure. Okay, so now we're going to print our data frame again, making sure our engineered feature is contained, and it is. It's right here. Okay, so now we're going to start cleaning and preparing our data set. I am dropping the name and gender column because it's just not, we don't need it for this demonstration. And I am assigning the salary string to our target. We're dropping employee ID, salary, and location too. So I'm doing that. And we have our columns. So I created a string array with all the columns that I'm going to be iterating through, because we have some categorical data here, and so I'm going to have to hot encode this data so that we're not dealing with any strings or anything like that. Okay, but that's for later. So here, right here, we're just going to visualize our features in our data set. Okay, so here we can see that age is very correlated to salary. We have the distribution of our department to salary, job title to salary, experience in years to salary, our education levels. And here is the end of year evals. And as we can see, there's almost a 1-to-1 correlation to salary. So when we are creating our model in the preparation stage, this is one of the stages where if we see something like this, we know that there is either a cause and effect. This is suspicious, so we have to investigate if there's a cause and effect situation, or if we have data leakage, if we're introducing future information into our data set. So this is why visualizing our data is very important, especially if we're engineering features, to ensure that we are creating features that do not create models that aren't good in deployment, that aren't useful in deployment. Okay, so as I discussed earlier, we need to hot encode our data set. We have some string variables. So here I define a function to return the codes for the categorical data. Okay. And here we're just, let me make sure I ran this. And here we're running our hot encode. We're iterating through all of the columns that have a string data type, and we're one-hot encoding them. So like job title was string, but now it's an integer. Okay? Am I going too fast, by the way? I just want to make sure that let me check in. Oh, okay, perfect. Oh no. All right, so let me continue. All right. So, all right. So now that we've one-hot encoded everything, now we are going to train. We're going to split our data sets. So I'm creating two models. I'm creating model 1 that will include our engineered feature, and model 2 with just the original features. Okay, so here I'm dropping just the salary column and assigning the salary column to our target variable y. And we are creating the x1 variable to contain our features. And for model 2, we have x2, where we're dropping the salary and end of year evals columns. Okay, and we're training our data set. We're splitting our data set here. So here we're doing that, and here we're doing that. So as you can see, we have x-train 1, x-test 1, y-train 1, right? And then we have x-train 2, x-test 2. Again, the features ending in 1 correspond to the model that includes the engineered feature, and the features ending in 2 are the original features. But it's okay, we're going to visualize our data and our model, so it will be easier in a little while. Comparing linear regression models, right? So now we're training our models with linear regression. We're importing linear model from scikit-learn, and we are creating our model, we're fitting, and we're generating our predictions. So this is for model 1, and this is for model 2. Okay, and we're getting the metrics. We're importing our R2 score, mean squared error, absolute error. So well, I shouldn't say R2 score, R squared score. Our R squared score is the standard accuracy metric for linear regression in scikit-learn. It is the coefficient of determination and explains model variability, with 1 indicating a perfect fit and 0 indicating no correlation to data. So it is the adjunct accuracy score in scikit-learn for linear regression. Okay, so here and I think I've already ran it. So here we have our model 1 evaluation. Our R squared score is 1 because it is completely fit to, the model completely fits to the data. And we have an absolute error of 3.439 times 10 to the negative 9, which is essentially 0. And we have a mean squared error of 1.571 times 10 to the negative 17, which is also essentially 0. But see here, model 2, which contains our original data, has an accuracy score of 0.89. 0.89, if we round it up, 0.90. And we have a mean absolute error of 11,535.33, which is a big difference from 0. And we have a mean squared error of 216,295,310.14. So our R squared score difference is 10.26%, which can be significant, especially with big numbers. All right, so let's visualize our model metrics here. So here's our leakage R-squared score for which is all the way up there at 1, and our original is very close to 90 or 0.9. Our mean absolute error for our leakage model is 0, but here, like I said earlier, our original absolute error is almost at 12,000. And our mean square error for our leakage is 0, and our original is all the way up there. Right, so this is when we're creating a model, this is one of the visualizations that would indicate that we have data leakage and that we would need to go and reevaluate our features and maybe implement regularization to decrease some weights. Okay, so now we're going to compare feature importance with SHAP. So if you haven't heard about SHAP, SHAP is a model agnostic feature API used in explainable AI. It can get a little bit complex, but today the focus of our usage of SHAP is just to compare feature importance. I'll probably do an event surrounding SHAP in the future. Maybe it'll be our next one. So here we are importing SHAP. We are creating an explainer variable with linear explain. We're passing model 1 and our X dataset are with model 1. And we're generating our SHAP values. And we're just suppressing some warnings here. And we're creating a plot with our SHAP values, our dataset for model 1. And here we go. So here we can see for model 1, it doesn't even tell us the feature importance for any of the other features, because end of the year is just all it cares about, since it's completely fitted to the model. And this would be a huge indication that something was wrong. Okay, and so for our model 2, which only contains the original data, this is a very healthy feature importance visualization, right? We see the variability and feature importance. We have our experience in years, age. Our experience in years is the most influential feature. Then second to age is second, education level comes third. So this looks like the more standard feature importance visualization. This looks very unhealthy, and this looks very healthy. All right, so in conclusion, what impact does leakage have what impact does leakage such as this have on an organization? So the impacts are unreliable insights and findings. An example, this demonstration created a 10.2% difference in accuracy, which can be destructive. So for example, if our target variable is extremely large, such as millions in dollars or pounds, we're trying to predict the cost of supplies for an organization. It can create potential loss in profits because we have a 10.2% accuracy deficiency in our model. So this example showcases an overfitting symptom of data leakage, where it is overfit to one feature that completely explains the target variable. But it is also possible for the symptom of data leakage to be an underfitted model. So in this scenario where the target is in a scenario where the target is projected demand, an underfitted model will leave an organization ill-equipped to meet up to the actual demands. So it can be very destructive. Another impact is inflated performance metrics. So as the graph that we showed above, leakage model's error is negligible. So I'm talking about this right here. Our leakage mean absolute error and mean squared error is negligible. So if we deployed a model like that, we would expect to never have errors. So engineers are expecting perfect accuracy and will share that with analysts who will in turn present that to stakeholders. This leads to disappointment when the actual MAE is almost 12,000 and our mean squared error is over 200,000. So that's just a disappointing reality after a model has been deployed. And also, it's a waste of resources. Once a model is deployed with a significant amount of error, unpredicted error, we would have to go back and retrain our data and fix the data leakage, create a new model, and sometimes retrain models from scratch. This is extremely computationally expensive, and it just utilizes a lot of resources. All right, so in conclusion, according to IBM, a National Library of Medicine study found that across 17 different scientific fields where machine learning methods have been applied, at least 294 scientific papers were affected by data leakage, leading to overly optimistic performance. Okay, so many are very quick to blame model engineers for data leakage, and to some extent this is true, but it is a very common mistake. As discussed, there are lots of preventive and mitigative measures that can be taken, but if you don't remember anything else, just remember to always double check feature availability of use cases after deployment. And make sure you're not introducing future data into engineered features. Okay. So thank you very much. This presentation is managing data leakage, mitigation and prevention techniques. My name is Arwa. This presentation was sponsored by Neural Transformers and presented by Miami Machine Learning. And if you have any questions, you could always email me. My email is arwa@neuraltransformers.org. Okay, so I'm going to stop presenting. So hi Josh, did you have any questions? Okay. Okay. All right, sounds good. I really appreciate you joining me today. And I hope to see you at our next event. Thank you and have a great day.